Okay, so yeah, like I had said earlier, I just had this bad vibe while we all were taking the test. I could kind of sense the struggle. So, I'll grade these. I'll probably have them done by tomorrow night at the latest. I'll try and get them done today. And then you can evaluate where you are in the class. We have Thursday as the deadline to drop. So if you wish to drop the class, the easiest way to do it is to email me and just officially, through Canvas, request to be dropped from the class. And I can do it electronically. All right, but Thursday's the deadline. So let's go through this. The first one, find the area under this curve on the interval 1 infinity. And so you first had to do some sort of integration technique to get this integrand to work out. So integration by parts would work. And then you work that out, and your antiderivative is right here. And then you have to take the limit and let t go to infinity. So when you do that, you're going to have an infinity over infinity here, which is going to require just a little L'Hopital, and then that goes to 0. So eventually, when you work this all out, you get 1/9. So I'll post these answers. You can look at them later, but I'm just kind of giving you the gist of how it works. So you should get 1/9 on that one. The next one, again, to do this one, you would have to do partial fractions. It's a pretty straightforward partial fractions. And then find your antiderivative. Oh, also, sorry, I should have pointed out that on the interval -1, 1, this function is discontinuous at 0. Has a discontinuity. Because if you plug in 0, you get division by 0. And so that means you have to break this integral up into 2 pieces. -1 to 0 and then 0 to 1. And then work it out. And when you do this one, on the first integral, when you try and plug 0 in, you get basically -infinity for, it's a limit, but I didn't show it. This is going to become -infinity, which means the whole thing diverges. As soon as you get to that, you're done. All right, sketch the region. I don't know how accurate my region is, but I do know that these two graphs intersect each other at 0 and 2. And then the formula for area is the top function minus the bottom function. And I think it works out to be 8/3. Next one is the region you had to rotate. You had to be in the first quadrant. That was important. So we were talking about this yellow region here. And you're rotating it around y equals 12, which is horizontal line. And so here's your little sliver. You have to find an outer radius and an inner radius and figure out what they are. You just use what we did in class for that, right? And then the formula is, did I forget my pi? I forgot my pi. I went real quick through this. Pi, and then what? The outer radius squared minus the inner radius squared. That's all I wanted was the setup. Here's the intersection. You had to find the limits of integration, so you had to set the two functions equal to each other. It was a pretty simple quadratic. You actually didn't even have to do anything like factoring or anything like that. You get 2 solutions, but only one of them is in the first quadrant. So, and then you take that same region, and instead of wrapping it around the y equals 12, you're wrapping around x equals 6. So that's out here. So for that, you'd probably want to use shells, the other method. So the formula for that's a little different. It's 2 pi times the radius of rotation, which would be the distance from the sliver to your axis of rotation, which is not x, it's actually 6 take away x. And then the rest of it is just the top function minus the bottom function. No squaring or anything there. All right, so this one, you have the base of a solid, right, is given here. And the perpendicular cross sections are semicircle. Semicircle is a half circle. So this is what it looks like. And so you want to find the volume of one of these little slices. So the area of a circle is pi r squared. Half of that is the semicircle. So half pi, here's the radius squared. And the radius comes from the top function minus the bottom function is your radius. Half. Yeah, I didn't put the 2. You have to do over 2. This is diameter, right? Your radius is half the diameter, so throw in 2. I was just working through this really quick to try and make sure that there wasn't any crazy things that were going to happen. And then that's it. And then, the integral goes from 0 to 4. Oh, you had to find this intersection, right? You had to find where they intersect. So you have to set these two equal to each other. This was a quadratic. It did factor. You get 2 solutions, 1 and -1. I mean, 1 and 4, but 1 doesn't work. 1 is a extraneous solution, so only 4 is correct there. And let's see. Length, arc length. Here's your function. The derivative turned out, after a little chain rule, to be this, and then you square it, which means you get 1/4 x squared, and then squaring this, the root goes away. Then you put that underneath the root, add 1 to it, get a common denominator. When you get the common denominator, really good things happen, because the numerator here is a perfect square trinomial. Or it looks like a perfect square trinomial, so it factors to be this. And then you can do square root top and bottom. Comes out to be a real nice polynomial. Integrate. Done. Next one, find the surface area of rotation. And here's the function. So you need the derivative. Again, chain rule. Cleaned up the derivative, squared it. Here's the derivative squared. You plug that in here. Here's the formula, right? It was 2 pi integral y, or the function of x, times this thing, which was the arc length. So you get a common denominator again. Good things happen again. Real good things happen. Eventually, these roots just cancel completely. And you wind up with just pulling out constants and just having to find the antiderivative of 1. So it comes out to be 12 pi. Formula. All right, alternating sequence. You have it changing signs starting with the positive, right? So I put a -1 to the n plus 1. That'll give me alternating starting with positive, then negative. And then these are even numbers on top, starting with 4. So I use 2n plus 2. Right, now we are assuming n starts at 1 for all of these. If you wanted to start n somewhere else, you could, but you would have to specify it. So 2n plus 2 should create my even numbers starting at 4, right? The bottom, the denominator, these are all powers of 5. It's 5 to the first power, 5 to the second power, 5 to the third power, 5 to the fourth power. So 5 to the n power, that'll create the sequence. Yes? Next one was a little harder. All right. The numerators. If you just write all these numerators out, these are all your odd numbers starting at -5. So it's -5, then -3, then -2, then 1, 3, 5, 7, right? So the numerator are just your odd numbers starting at -5, so I use 2n minus 7 to do that. And then you had to realize, this was the tricky part, this -5 was -5 over 1, the -3 was -3 over 1, and then 2 is 2 times 1, 6 is 1 times 2 times 3, 24, 1 times 2 times 3 times 4. So you realize that all these denominators are factorials starting at 0 factorial. So when you plug in 1, you need to get 0 factorial on the bottom, which is why I use n minus 1 factorial. All right, you plug in 1, you get 0, plug in 2, you get 1, and it generates this sequence. This could have been a little bit more difficult. I could have made this a little more challenging had I actually reduced this fraction, right? If I had made that 1/8, if I had reduced this one, it might be a little bit harder for you to have seen that pattern, but I left them unreduced so that the pattern would be more obvious. Okay, is that it? Oh no. Okay, for this one, do these sequences converge or diverge? They both converged. This one was just an exercise, make sure you knew how to do the factorials, how to peel things off. So you break down the bottom factorial, you cancel out, and then here you let n go to infinity, right? And you get 0. So this converges to 0. This one, it's infinity over infinity, so you have to look at this as a function of x first. Like you can't do L'Hopital's rule on a sequence, so you look at it as a real valued function. You have to apply L'Hopital's rule 3 times, and when you keep doing that, eventually you get 0, which means you can conclude that the original sequence goes to 0 also. I didn't do the bonus. Okay, but I mean, it was that problem, and you can show that it's increasing and bounded. Bounded, you have to show it's bounded on top and the bottom. And then I say, does it converge? So, does it converge? I have an increasing bounded sequence. Yes, there's that monotonic sequence theorem, bounded monotonic sequence theorem. Theorem says that if you're increasing, that means you're monotonic. And then if you're bounded, well, that means you're bounded on top and bottom. And the monotonic bounded sequence theorem says that if you're bounded and monotonic, then you must converge. So the answer to that would have been yes by the monotonic bounded sequence theorem. All right. All these problems came right out of the book. Right out of the book. But they were out of chapter review. So I just want you to know that, because I don't want you to be sitting there saying, you know, he pulls the hardest problems that he could possibly find, and because that's the usual comment I get after tests, that my tests are nothing like anything else, and it's crazy math I'm trying to give you. So now you have some idea of where my problems come from. All right, well, I will grade these. I have in the back of my mind that I'm probably going to throw out 1 or 2 of them. So find your best 8 and grade those. But I just need to see how everyone did first. All right. Any questions or comments? All right, well, last time we were talking about series, right? I don't know how much of this stuff you remember, because you're probably getting ready for this test. But the idea was that a series is just the sum of a sequence, right? You have a sequence of numbers, you add them all up. Our biggest question is whether or not a series converges or diverges, right? That's our big question. So the big question for us is, does a series converge or diverge? Anybody remember what series we ended with last time? What it was called? Geometric series? Does a geometric series converge or diverge? It depends, right? Geometric series can converge and it can diverge. It just depends on the series itself, right? It depends on that value of R, which we have to identify. But before we actually continue, because I want to continue with a little bit of geometric series, I want to state another kind of theorem for us. Where is it? Come on. Oh, there it is. This is going to be, I handed out a formula sheet for you, right? This is, you are allowed to use this on the test. Consider this to be a big Christmas gift, okay? Because when I was a student, I had to know all these walking into the test. I was not given a sheet to go reference off of, all right? So I'm allowing you, because it's summer school and, you know, I'm giving you kind of a little break here. You don't have to memorize all these tests, but you need to know how to use them properly. So what I'm going to be referring to right now is the first test on this sheet, which is called the Nth Term Test. Remember, the big question is, does a series converge or diverge? We've seen that it can It can converge and it can diverge, but it's just hard to tell when it happens. So the nth term test is usually the first test that you ever try when you're looking at a series. And what does it say? So it says the nth term test and the series that we're looking at. If you're looking at some series, A sub n, the sum, A sub n, that's the notation that we'll use. What they mean by this is like n starts at 1 and goes to infinity or something like that. I mean, you have a series, right? There it is. The nth term test says, take a look at the actual sequence inside. Go look at that. Bring it over here. Take the limit as n goes to infinity of just the sequence, all right? Just the sequence. If that limit does not go to 0, what's the conclusion? It diverges. What diverges? The series diverges, all right? The series diverges. This is a nice test because it's very simple to apply. Remember on the test that you just took, the last, second to last question, or last question, I said, does this sequence converge or diverge, right? And what did you do? You took the limit as n went to infinity. We're talking about series now, which are completely different than sequences, but it turns out that if you're looking at a series and the sequence itself, if that sequence does not go to 0, the series diverges automatically. Now, what if it does go to 0? What if this limit does go to 0? What does that tell you? Nothing, okay? That means you don't know. That means it could diverge, it could converge. You understand? There's logic involved here. If it doesn't go to 0, diverges. If it goes to 0, you don't know. I'll give you an example of something like this. What if you want to find this? What does this add up to be, right? You're going to add these things up forever. So let me ask you first, geometric, does it look like a geometric series, what we studied last class? Why not? What is it that we had with geometric series? Yeah, the n, right? The index here, the n, the variable you could say, was actually in the exponent of a number, right? We had r to the n. Here, the n is actually just like in a polynomial, it's just in a base. So this definitely does not look like a geometric series. So the first thing I'm going to do is I'm going to apply the nth term test. I'm going to look at the inside, come over here, I'm take the limit as n goes to infinity of 2n plus 1 over 3n plus 2. And what's that, infinity over infinity? So you could apply L'Hopital's rule one time. So what would this turn into after some L'Hopital rule? 2/3. So look, as we move ahead, all right, you are not going to need to show me L'Hopital's rule here. You can just say 2/3. That's okay with me. All right? So that limit is not 0, is it? What does that mean? That means that this series does what? Diverges. And you're done. It can't diverge and converge at the same time. So it diverges, we move on to the next problem. So it's a very convenient test, but it's very limited also because there's other series that, like this one, okay, find this series, does it converge or diverge? So we go to the first test that we have, the nth term test again, right? Take that over here. We take the limit as n goes to infinity of 1 over n plus 1. What does that equal to? 0. What does that tell us about the series? Nothing. All right? Somebody on the test is going to say the answer is 0, therefore the series converges. Or they're going to say it converges to 0 or something like that. That means there's a huge disconnect. I remember last semester, the lecture after this lecture, I gave a quiz in the very beginning of class. I gave a problem like this, converge or diverge, and almost everyone in the class, almost everyone said the answer was 0. That means there's a total disconnect. This test, when you get 0 here, tells you nothing. So all you could say at this point is nth term test fails. All right? That's it. Fails. So that means you don't know if this converges or diverges, and that means you have to go to a different test. But we're not there yet. That's what the rest of today and next class will be, is getting through all these tests. All right, understand? Questions? All right, now, back to the geometric series. Take a look at the geometric series on the formula sheet. It says that if you have a series, sum n equals 1 to infinity, a r to the n minus 1, that should look familiar from last class. That there were two different scenarios. It converges, and actually we can find the sum. The sum is s equals a over 1 minus r, as long as the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than 1. So make sure that when you're applying this test, you're looking at a series that fits into that format, a r to the n minus 1. If it doesn't look like that, you can't use the test. So I wanted to show you one more thing with geometric series that I didn't get a chance to do last time. All right, so I'm trying not to go off on a tangent too far here, but if you take the number line, right, and you were to go in here and just randomly pick a point, right, and let's just call that C, that's a number, all right? I'm just going to pick that constant out of there. That number can be one of two things. It could be a rational number, or it could be an irrational number. Rational or irrational. A rational number is a number that can be represented as a fraction. A lot of people think that any number, if you pick it out of the number line, there's always a fraction that corresponds to that number. That's not the case. The fractions make up a lot of the number line, but there's a lot of other numbers in there that are not fractions, that you cannot represent as a fraction. An example of a rational number, I mean, you know rational numbers, 1/4, 2, 1/3. Those are all rational numbers, right? -10. Those can all be written as fractions. Irrational numbers are like pi, e, square root of 2. The difference between these two sets of numbers is that if you fall into this category, right, then if you write that as a decimal, not as a fraction, one of two things have to happen. The decimal either needs to terminate, or if it continues forever, it has to have a pattern. I'll give you an example. I'm going to write these underneath this. 1/4 can be written as what? 0.25. 2 can be written as 2.000, right, forever. 1/3 can be written as 0.333 forever. I'll put a line over the 3. -10 can be written as -10.000. All of these have something in common. The decimal either stops, 0.25, done, right? There's zeros at the end that keep going, but that we won't count that. Or it repeats with a pattern. Every fraction can be written this way. These over here cannot. Pi is what? 3.14, and then there's no repeating ever, right? It just keeps changing, no pattern to it at all. Same thing with E, same thing with the root 2. Understand the two categories of numbers that live on the number line? How many rational numbers are in the number line? How many of them are there? A lot, right? Infinitely many, right? Infinitely many. How many irrational numbers do you think are in here? Infinitely many. There's actually infinitely many of both. However, if you go on and do more math, which I know some of you are maybe planning on doing that, there's actually two types of infinity. There's what's called countable and uncountable. So the rational numbers are what we call countably infinite, and the irrational numbers are uncountable. And what's interesting, even though I've already gone off on my tangent, but what I find most interesting about this is that if you were to actually close your eyes and reach into the number line and go and grab a number, the probability, okay, like, you know, when we flip a coin, probability, heads, tails, right? The probability of picking a fraction, a rational number, the probability is 0. That is kind of a crazy idea because there's infinitely many fractions in there. But there's just so many more of those. And I know that doesn't make sense, but that's what we mean by two types of infinity. So anyways, all right. If every rational number is a fraction, and every fraction can be written as a terminating or repeating decimal, then I should be able to give you a decimal that repeats or terminates, and you should be able to turn it into a fraction, right? I should be able to give you this, and you should be able to turn it back into this. I know on calculators there's a key for it, right? It says like decimal to fraction, or fraction to decimal, or something like that. So I would like us to do this problem. I would like for us to take 0.27, I'm going to just do one that I've done already. Well, I'll just make one up. 2755, no, change it, 545454. Everybody agree that that's a decimal? Does it ever stop? Okay, is there a pattern to it? Yes, that means it's a fraction. Tell me what the fraction is that gives you that number without hitting it on your calculator. All right, here we go. So I want to convert this to a fraction. I know you may be sitting there going, why in the world would I ever want to convert that to a fraction? But this is an exercise with geometric series. So do you agree that that decimal up there is, this 2 right here is 2/10, right? 2/10. Then you're going to add to that this part, which is what? 7/100ths. And then you're going to add to that, what? 5/1000ths. And then to that 4/10,000ths, and then 5/100,000ths, and then 4, where are we at? We at million? And then this keeps going, right? Yes? All right, the pattern is on the 545454, right? This 2/10 and the 7/100th does not change, right? Everything else is going to keep, I'm sorry, I should say these two are just there. This stuff is where our pattern recognition needs to come from. So I'm going to really focus a lot of my attention right now on this. And what I'd like to do, since it's 545454, I'm going to put these two together, and I'm going to put these two together, which means I need a common denominator. So what's another way I could write this right here? I could turn this 1,000 into a 10,000, couldn't I? Multiplying top and bottom by 10, which would be 50 over 10,000 plus 4 over 10,000, which is 54 over 10,000? Agreed? Now these two together, what would that be? 54 over a million. What would the next one be? $54 over 100 million? What's happening every time I go out? I have, what, 4 zeros here, then I have, what, 6 zeros here, then I have, what, 8 zeros here, next one I'll have 10 zeros? So I could also look at this as 54 over, isn't this 10 to the 4th, plus 54 over 10 to the 6th, plus 54 over 10 to the 8th. The next one would be 54 over 10 to the 10th, and so on and so forth. Yeah? That would be correct? You following it? Can you give me just this red, and please do not forget, we have to come back and address this up here. But just in red, can somebody write this in sigma notation? This is equal to what? Sum n equals 1 to infinity. What never changes? 54, okay. And then the denominator are powers of 10, starting with what? 4 and then 6, 8, 10. So I need to count even numbers starting at 4. How can I count even numbers starting at 4? 2n plus 2. So 10 to the 2n plus 2. We'll count those out. Everyone agree that that would be the rest of it out there? Now I think I'll throw the other part off the beginning here. I had the 2/10 plus the 7/100, right? And then I have plus this red thing. All right. What type of series does this look like? Well, where is the n? It's up in the exponent, right? So what I'm hoping for is that this is geometric. But for geometric, remember what we need is this. Sum n equals 1 to infinity. We need an a. We need an r to the n minus 1. What do we think? Well, no, I don't want that. Can we get this to somehow look like this? Can we? How about the 54? Do I need it in here? It's a constant. I could just slide it out right here in the front, or I could slide it outside the sum. It doesn't matter. I think what I'll do is I'll slide it out. I'll keep it in the sum. I don't have to, but I will. 54 times, and then I'm going to rewrite this as 1/10 to the 2n plus 2. Now you tell me if you agree. Is that the same thing? Yes? Because when you take 1 over 10 and raise it to this power, you raise 1 to the power first, which is going to just be 1, and then you raise 10 to that power, which is the bottom. So I've just kind of recognized that this 10 to the 2n plus 2 on the bottom, there's really a 1 on top of it, slid the 54 out. Got it? Is this starting to look more geometric? Do you have an R? Do you have a candidate for R here? Yeah, what do you think R is? 1/10? It's looking that way, right? The problem is this does not look like this, and it must look like this in order to use the formula. So I need to turn 2n plus 2 into what? n minus 1. And now we get to have some massaging fun. We talked about this a while back. We want to try to change something from looking like one thing and turning it into another. So let's see. And I really need an n minus 1, don't I? I'm going to first address the issue of us having a 2n. I don't want 2n, I want n. So watch what I do here. Is that the same thing? right? If you have the same base and you're multiplying these together, you would add the exponents, wouldn't you? And so all I'm doing is rewriting this single factor as these two factors. And then I'm going to do something else. It's one of those problems where you kind of want to watch someone do it that first time, and then now you kind of know what you need to do. I'm going to take this right here. I'm going to square it, right? 1/10 squared is 1/100th. I'm going to put that over here with the 54. So 54 over 100. And then this is going to be 1/10 squared to the n. Now, do you believe that? 1/10 to the 2n is the same as 1/10 squared to the n. Because if you have something like 1/10 and you raise it to the second, then you raise it to the n, what do you do with these two powers? Multiply them, right? And 2 times n is 2n. So I'm actually just kind of like extracting the n out of there, but I have to rewrite things to do it. What's 1/10 squared? 1/100th. So I actually don't want to write that whole line again. So I'm just going to replace this with 1/100th. So from here to here, I did 1/10 squared to the n. Y'all still with me? Now does it look geometric? Almost. What do we need? N minus 1. So if I don't have minus 1 here, how do I make it a minus 1? Minus 1 plus 1. So I'm going to come in here and add and subtract at the same time. I have 54 over 100 here. I have 1/100th to the n minus 1 plus 1. I'm about to erase this plus 1. I just want you to see what I'm doing. Everyone see what I'm doing? N is the same as n minus 1 plus 1. But if I split this like that, then I could have written this as 1 over 100 to the n minus 1 times 1 over 100 to the first power. So watch what I do. 1 over 100 to the first power. Do y'all see that this is the same thing as this? Same base, add the exponents. When you add the exponents, you get n. 1/100th to the first power is just 1/100th. Bring that over here, and that would become 54 over what? 10,000? One 100th to the n minus 1. There it is. That right there is a geometric series. It has the format sum n equals 1 to infinity of a r to the n minus 1. Does this series converge or diverge? It converges. Why? R, right? R here in this problem is 1/100th, right? The absolute value of R is obviously less than 1, isn't it? That means it converges. In fact, because it's a geometric series and because R is less than 1, we actually know what it converges to. What is this yellow thing turn into? A over 1 minus R, right? That's what it turns into? So I'm out of room. I'm going to go to the next page. What's A in the problem? Sorry, I didn't label it. A was what? 54 over 10,000? Right, there's your A. There's your R. All right. Next page. Can I go or no? So we have, what was it, 2/10 plus 7/100 plus A, which was 54 over 10,000 over 1 minus R. R was 1 over 100. This is 2/10 plus 7/100 plus 54 over 10,000 over what's 1 minus 1/100? 99/100. And now you can flip the fraction, right? Flip it. So you get 2/10 plus 7/100 plus, what does this turn out to be? Was it 5,400 over, is that right? When you flip this fraction up, 100 times 54, isn't that 5,400? And then the 99 comes and hits this, 99 times 10,000. Is going to be, is that right, 990,000? Okay, we're almost there. All I need now is put these fractions together. Get a common denominator. What's my common denominator? Well, let's clean it. Can we like take 2 of these zeros out at least? Can we do that? Over there? All right, what's our common denominator? 9,900, right? How do you turn this into 9,900? Multiply by 990, 990 on the top and on the bottom. So what's 990 times 2? Help me out here. 990 times 2? Oh, like divide by 2? Yeah, you could, I guess. Yeah. You want to do that? I don't care. You want to simplify that? It should all be the same. I mean, we can reduce it later. What do you all want? Reduce or not? Reduce this now or not? Yes or no? No? Okay, so multiply this times 990. What's 2 times 990? Okay. Was it 1980? And then plus, so I'm going to have a common denominator, so I'm not going to write the denominator here. I have to multiply this one times what? 99? What's 7 times 99? 696 what? 93, that's what I thought. All right, 693 over the common denominator, and then plus 54 over the common denominator. Check it. Add these up. What's 1980 plus 693 plus 54? Who's got that for me? I don't feel like doing arithmetic. What is it? 2,727 over 990? 9,900? All right, type this into your calculator. Get a decimal. .275454545454. That's it. All right. This is a good test problem because it involves quite a bit of stuff here, right? You got to be able to break a decimal down and know what it means. You got to be able to find the pattern, put things together, recognize what's happening here, convert it into a series. So this is basically me giving you, almost like giving you a sequence and asking you to find the actual function for it. Then once you get that, you got to make it look geometric, which means you have to demonstrate the ability to manipulate all the exponents. And then once you get to that, then you apply it, and then at the end, put your arithmetic common denominators put together. Great news is that you check your answer very easily, right? You just get your answer and check it on your calculator. Okay. All right, I think that's it with geometric series. We're going to move on to the next type of series, which is called harmonic. And notice on your tests, you do not see harmonic on here. And here's why. Right now, we only have one other series that we know how to handle, and that's a geometric series. If we have a geometric series, we can actually figure out if it converges or diverges. We've got that. Harmonic is our second type of series that we need to be familiar with, and it looks like this. It's any series, n equals 1 to infinity, of, I'm going to put C on top over n. C is a constant. So let me show you an example of a harmonic series. The series 1 plus a half plus a third plus a fourth plus a fifth plus dot, dot, dot. What I want you to recognize with a harmonic series, this is extremely important with harmonic series, is notice that the n, the thing that's under control, right, by the index, is in the denominator, right? N doesn't appear anywhere else. It's not in the numerator, right? It's not in an exponent. It's in the denominator. And this is linear. That's a linear expression, right? N. If that said n plus 1, that would still be linear. It would still fall into the category of harmonic. All right? If that said n plus 2, it would still be harmonic. If it said 3n plus 5, it would still be harmonic because it is linear. So we have this happening. Our numerators are all staying the same, right? 1, 1, 1, 1, 1. So it's a constant. That could be 3, 3, 3, 3, 3 up top. Doesn't matter. But the denominators are going up in a linear fashion. Every time you move out, it goes up by the same increment, right? 2 becomes 3, so it jumps by 1, right? 3 becomes 4, it jumps by 1, jumps by 1. If this happens, then we need to figure out what the heck's going to happen, right? So this specific series, right, this one right here, the example I'm giving you, if I were to write that in sigma notation, it would be just 1 over n, wouldn't it? That's the actual expression for it. If that was given to you on a quiz or something, the first thing that you would do is you would check the Nth Term Test, right? The Nth Term Test. What does the Nth Term Test tell you? You take the limit as n goes to infinity of the sequence, right? The actual definition of what's inside the series is 1 over n. What does that limit go to? 0. What does that tell you? Nothing. Fails. Right? So that would be your first kind of attempt at it. You would say it fails. You can't use a geometric series because it's not a geometric series. So what else do we use? Well, it turns out with harmonic series, at this point, the only way I can convince you of what it does is hopefully by helping you see some sort of pattern of what's going on here. All right? So I would like for you to focus your attention up here on the series written out. 1 plus 1/2 plus 1/3. What I'm going to do is I'm going to clump these two guys together. Then I would like to do clump the next 4 together. The next 4 would be 1/4 plus 1/5 plus 1/6 plus 1/7, right? And then I'm going to clump the next, what do you think? First I clump the first 2 together, then I clump the next 4 together, then I'm going to clump the next, it's either 6 or 8. It's actually 8, okay? So I'm going to take the next 8 and clump them together, which would be 1/8 plus 1/9 plus 1/10, plus 1/11, plus 1/12, plus 1/13. I'm going to run out of room, plus 1/14. Where am I? 1, 2, 3, 4, 5, 6, 7. One more. Okay, and then this thing keeps going, right? Plus, 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 plus. What would I clump together in the next one? What do you think? The next 16. If you keep doing that in on powers of 2, watch what happens. Put these two together. You would need a common denominator, right? What would the common denominator be? 6, right? So what would this be if I put these together? 5/6? Yes? Okay. And then what about this over here? Oof. You have to get a common denominator, right? Let's just try it. Someone get a common denominator. I'll help you out. Multiply all the denominators together. That'll be a common denominator, right? 4 times 5 times 6 times 7. What, 840 would be a common? So this would be, to rewrite this 840, you'd have to multiply the top and bottom by 210 on top and bottom, which would give you a 210 plus, here you'd have to multiply top and bottom by 168. So you get a 168. Oops. The next one would be 140. And the next one would be 120. Add all those up on top. What is it on top? Someone get that already? 319 over 840. Does it? No, that's 638. Okay, we could keep doing this, but this looks like it would be exhausting, right? So there's something else I want you to kind of pay attention to here. I think it'll make it a little bit easier for us to see what's going to happen. Do you agree with me on this? I'm trying to pick a color here. This right here, all right? Do you agree that that's bigger than 1/3 plus 1/3? Or you know what? Yeah, is it? Is it? Yes? Which is what, 2/3? How about these together? What can you say that this is bigger than? 1/4. Is 1/4 bigger than 1/7 or smaller? Bigger, bigger, bigger. These are all bigger than 1/7, aren't they? All bigger than 1/7? So to have 4 of these would be, this is bigger than having 4 1/7. So would you agree that this over here is bigger than 4/7? Yes? The next one would be bigger than having what? 8/15. Yes? You following this pattern a little bit? But each one of these, all of these, right, are bigger than 1/2, aren't they? Look at this. Isn't 2/3 bigger than 1/2? 4/7 is bigger than 1/2. The next one's bigger than 1/2. The next one should be bigger than 1/2 also. So what we're going to get to as a conclusion is if we write this out, I'm going to write therefore, and this is not a formal proof, but it's enough for us to move on. 1 plus a half plus a third plus a fourth forever is bigger than having a half plus a half plus a half forever, isn't it? A half plus a half plus a half forever. But a half plus a half plus a half plus a half diverges, doesn't it? Doesn't this diverge? Because this is the same as sum n equals 1 to infinity of a half. See, n has no control over this. And what do we say? If this does not go to 0, right? If this thing does not go to 0, what does the series do? Diverges, right? So what we're saying is this series, the harmonic series, has to be bigger than a divergent series, which means it has to be bigger than infinity, which means it has to be infinite itself. So that is the conclusion. All harmonic series diverge. Done, end of story. That's the somewhat of an illustration as to why. So conclusion, all harmonic series diverge. One more example of harmonic, just so you can recognize it. Sum n equals 1 to infinity of pi over e times n plus 1. Sorry, that e is the exponential e times. So that's like 2x plus 1 or 2n plus 1. E is just a number, right? So you look at that. First thing, nth term. What does nth term tell you? That thing goes to what? Goes to 0, right? If you let n go to infinity right here, it goes to 0. That tells you nothing, right? That fails. Okay, the next thing I would do is say, oh, is it geometric? No, the n is not in an exponent, so it's not geometric. Next thing I know about series, harmonic. Is it harmonic? Do I have a constant on top? Sure. Is the bottom linear in n? Is it linear in n? Yes, this is harmonic series. So it's harmonic. Since en plus 1 is linear in n. That's how we say that, right? Is linear in n. N is our variable. It's a linear expression in terms of n. It's linear in n. Therefore, the series diverges. So that's just a matter of recognition. But notice how I'm writing everything out? That's what I want to see, that sort of like thought process written out. All right. Next one. Next type of series. Next one is called telescopic or collapsing series. And I'll give you an example. We're going to start with an example. You take a look at it. First thing you do, nth term, right? What happens to that as n goes to infinity? What happens to the expression inside the series there? Goes to 0, which tells you nothing. I've had a test before where I've given a problem where this nth term test actually works, and you get like this is 1, and then you conclude what? Diverges. But the students will skip that. They'll forget about the nth term test because there's all this other stuff to worry about, right? So you start to lose focus when at the very beginning, if you would have applied that, you would have been done with the problem, and it would have taken you about 20 seconds instead of the 30 minutes that you fumble around trying to figure out what's going on when it diverged from the very beginning. So always be sure you're running through these tests. I'm not saying necessarily that you have to go in this order, but I would always caution you to think nth term test, first. All right, so is it geometric? No, because n is not an exponent, so we'll never be able to massage it to look geometric. Is it harmonic? Do you have a constant on top? Yes. Is your denominator a linear expression in n? No, it's quadratic, right? If you multiply that out, it's quadratic. It's not a linear expression in n. It's not harmonic. So it's got to be something else. Well, what we can try is to see if we can somehow rewrite this in a way that we get this thing that we're going to call telescopic or collapsing. You'll see when we work through the problem why we call it that in a minute, but let me work through it first. Do you agree I could do this? What do you think I just did there? What do I do to get from here to here? You've done it before. You did it when you were doing integration. It was on this test that you just took, partial fractions. You have to do partial fraction decomposition, right? You rewrite that thing. You figure out what A and B are, and then split it up. So these things don't ever go away. I mean, I guess, like on that last test, like integration by parts, that just because we tested over it doesn't mean it can't appear again. Partial fractions can appear again. It's going to continue to appear. So we got to be comfortable with it. You all think y'all could get that, right? I'm not going to go through the work, but you could do this to this, right? Y'all okay? What? You would have to find out what A and B are. If you would figure out that if you split this up, A is 1 and B is -1. Right? So if you split this up, it would be 1 over n plus -1 over n plus 1 if you do your partial fractions. And then, so what I'm doing is I'm just writing it this minus in the middle. Is that all right? You can always check it, right, real quick for me. Put these together, right? So you put an n plus 1 up here, you put an n up here, put these two together. You should get 1 over n times n plus 1. So that is the correct partial fractions. Now, how does that help us? Well, let's start writing out the terms of this series right now. So plug in 1 and tell me what you get. Plug in 1. First thing you get is 1 minus a half. Do not simplify that. But do you agree that's the first thing you get? Plus, now plug in 2. 1/2 minus a third. Y'all agree? Next one. 1/2, or sorry, 1/3 minus a fourth. Plus, I'll do one more. 1/4 minus a fifth. Plus dot, dot, dot. That's what it is, right? Now, if we had done this initially, like if up here if we had written this out and plugged in 1, I didn't write it, but let's just see what would happen. If I plugged 1 in here, what would we get? 1/2 plus, plug in 2 now. 1/6 plus, plug in 3 now. 1/12 plus, you see what I'm doing? And that would keep going forever. This right here, notice that there's no subtractions in here. You see that? So it's just this plus this plus this plus this. The thing is, these denominators are not going up linearly, like a harmonic was going up linearly. These are actually going up, but they're behaving in a quadratic fashion, which is why it's not harmonic, which is why you can't just say it diverges. But by doing partial fractions, what we do is we've luckily introduced a subtraction sign into this. And look at all this subtraction that's happening. This negative 1/2 is actually going to cancel with that, right? And this is going to cancel with this. And this is going to cancel with this, right? That's what's going to continue to happen? Do you all agree? So it looks like maybe the answer is just 1. Maybe. But to do this correctly, here's what we have to set up. We have to stop right now and recognize that we're getting cancellation. And we have to set up S sub n, which from last class is called the nth partial sum. Now, the reason why we're going to set up the partial sum is this. Recall from last class, that the actual sum of this series, we called it capital S, right? That is just the limit as n goes to infinity of the nth partial sum. So if we can find a formula for the nth partial sum, and then take the limit as n goes to infinity, we will actually have computed what this sum is. So what is S sub n? I'm going to write that down here, and then at the end of it, I'll take a limit. So S sub n is what happens when you start adding these guys up, right? But you stop somewhere, don't you? You actually stop at n. So I'm going to rewrite this sum right here, but I'm going to stop at n. So watch how it looks. It's 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus, now normally I would go dot, dot, dot forever, right? But this time I want to stop. So I'm going to come way out here. If my last one is the nth one, I'm putting an n above it so you know what I'm plugging in. If I plug n into this expression, right, then what would I get? Replace n with n, it's just itself, isn't it? So this last one will be 1 over n minus 1 over n plus 1. Agreed? Yeah? Now, when we're doing these telescopic series, it's always good practice to then go and look at a few more in front of this. So let's go and take a look. What is the guy right in front of this one? What would I be plugging in? Not n anymore. I'd be plugging in what? N minus 1. So I'm going to put that above so everyone knows what I'm plugging in. So what would happen if I replace n with n minus 1s in here? I'd get 1 over n minus 1. And the next one would be minus 1 over n minus 1 plus 1, which is just 1 over n. Let's go back one more. In this case, I'd be plugging in n minus 2, right? That's the one that's 2 in front of n. And what would that look like? 1 over n minus 2 minus 1 over n minus 1. Do y'all see this? Now, let's look at all the cancellation. I think this is a super obvious cancellation. The next problem won't be so obvious. This 1/2 cancels with that 1/2. This negative 1/3 cancels with this positive 1/3. This negative 1/4, is it going to cancel with is there going to be a positive 1/4 here? Yes, if n is big enough, that will happen, right? So that will go away. All right, how about this 1 over n minus 2? Is it going to cancel out? What kills this one off? The one before it, okay? So listen to the way I'm talking here, because, again, it's going to be very helpful in the next example. The pattern of killing that we're seeing here is like this. The second term in the first expression here is canceling with the first term in the next expression. Yes? The second guy kills off the first guy, the next one over. There's so many different ways you can say this. So second guys kill off first guys to the right. So that means first guys get killed off by second ones in front. So this guy gets killed off by the one in front. Yes? This is a second guy, isn't it? Second guys kill off first guys to the right. So this guy is going to get killed off over here, like that. Second guys kill off first guys to the right. So this guy's going to get killed off that one. Second guys kill off first guys to the right. Is there a first guy to the right? No, because we stopped, didn't we? This guy does not go anywhere. So we still have this piece right here. And what else didn't get killed off? The one in the very beginning. So that means that S sub n is equal to 1 minus 1 over n plus 1. Why do they call this a collapsing series? Have you ever seen a bridge collapse? Right? Everything in the middle goes away, right? And you've got the ends are still there. That's basically what's happening here. It's a series where when you're clever enough to rewrite it with partial fractions, then the sum actually looks like a bridge and everything in the middle collapses out. Telescopic, old school telescopes, you know, you've seen those? And what do they do with them when they want to put them away? Right? The ends come together, everything in the middle goes away. And understand? That's where the terminology comes from. Most of the time, not all the time. Let me see. I might have another example here. I know that there is a possibility you could have one with logs. Yeah, there's one with logs here. I can show you the one with logs. But it's usually going to be partial fractions or some property of logs. All right, so we're not done, right? We're not done? S, the sum, is the limit as n goes to infinity of 1 minus 1 over n plus 1. And when n goes to infinity here, this goes to 0, doesn't it? And so your answer is just 1. This adds up to be 1. That's your answer. So it converges, right? What was the first question that we discussed today? Like after the test, I said, what is the goal of series right now at this point? Does it converge or diverge, right? Converge or diverge. We've seen geometric series can do one or the other, right? If it does converge, can you tell me what the answer is? Yes. Harmonic series diverge all the time, right? Telescopic converge. Can you tell me what they converge to? Well, telescopic can do either one. It depends. But if it does converge, does it appear we actually have a numerical answer? Yes? After today, when we look at more series, we are going to lose the ability to actually find what they add up to be. We'll be able to say converge or diverge, but we will not be able to find the sum. So there, on a test, if I say find the sum of the series, I'm telling you it's geometric or harmonic. I'm telling you that. I'm sorry, geometric or telescopic, because those are the only two series we can actually find the sum of. All right, let's do another example. Oh, I want to go back through just the process, because on a test, again, it's very important that you write things down correctly. I'll take off if you don't. First thing you do, you know, try and figure out nth term works. Do your partial fractions. Of course, you'll have your work for that on the side. Then write out what the sum is. Discover your pattern, right? This was just pattern discovery here. That's all that was. The next step is to set up the nth partial sum. You must set the nth partial sum up on the test. You have to show me this stop somewhere. and you have to show me the cancellation. And then, from there, you can come up, cancel everything out, and then take your limit. All that has to be in there. You cannot just have written this down and put 1. If you do that, you're going to get in trouble because there's some problems where you work it out, and it's not always going to be just the number sitting in front. That's not going to be the only answer. So this was just to get us used to the idea of what a telescopic's doing. All right, try this one. You want a log one? We can do a log one. I'll show you the one I was going to do, and I'll let you do that one as an exercise on your own. I was going to do sum n equals 1 to infinity. No, 2 to infinity, sorry. 2 to infinity of 1 over n squared minus 1. Although we can take a vote if you want me to do this one. Do y'all want me to do this one, or you want me to move to a log one? Do y'all care? Huh? You want to see this one? Okay. All right, so I would first nth term test. What does nth term test tell us? Nothing, right? Fails. This thing goes to 0 as n goes to infinity. Do y'all see why I started the index at 2 and not 1? Right? Can't plug 1 in, you get division by 0. So start at 2, big deal. All right, if we were to start writing out the terms of this thing, right? If we did right now, we would get, what, 1/3 plus, now plug in 3, right? I plugged in 2 just there. Now plug in 3, it'd be what? 1/8 plus next one, 1/15 plus ... Notice that there's no subtractions in there. Since there's no subtractions, you're never going to get canceling here. So what we have to do is say, all right, maybe it's going to be some partial fractions and I can get subtraction. I've already skipped over. It's not geometric, it's not harmonic, right? Okay, so the good news is I can factor that. And that should be the tip-off for you that if the denominator factors, you should be able to do partial fractions. Now, I'm not going to show the work. 2. This should turn out to be, I think it's 1/2 and -1/2, or the other way around. It's -1/2 over n plus 1 plus 1/2 over n minus 1. Okay, so that's what you would get if you took the time to do partial fractions on it. All right? Is that okay? I'm not going to show it. Okay, now let's write these out. Again, I'm just going to try and discover a pattern here and hope for the best. Start out with n being 2. What would you get? -1/2 over 3, right? So the first one's going to be -1/2 over 3 plus the next one would be 1/2 over what? 1. Okay, that's what happens when we plug in 2. Now plug in 3. -1/2 over 4 plus 1/2 over what? What am I plugging in? 3? You get 2. Plus, just look at those two right now. Did anything cancel here? Nothing canceled. Okay, go out one more. Now I'm plugging in 4, right, for n? Get -1/2 over 5 plus 1/2 over what? 3? Anything yet? Ah, yes. Look. this one, and this one are going to cancel, aren't they? So now let's talk about this in terms of you see, this is different language, how you want to say this, however it makes most sense to you. I was saying in the previous problem, like the first guy cancels the second guy and the second one, right? That's what I was saying? All right, in this one, these are all females, so we're not going to refer to them as guys. Can you all tell the difference? No? Okay, so she is going to cancel with her over here, right? Yes? First ones cancel with second ones, but not in the next expression, but 2 down, right? That's what it looks like is happening. So the first one, for a first term to get killed off, there must exist a second term over here, but 2 down for it to happen. I'm going to write another piece over here to see if it continues this way. Negative 1/2 over what? 6 plus 1/2 over 4. Okay, we just said first ones require you to have something to the right of it, don't you? Second ones require you to have something in front of it. So this second one should get killed off by something in front of it, does it? Right there, yes? This one and this one. How about this second one? Second one should get killed off by ones in front of it, right? There's nothing in front of it. So this one shouldn't go away, should it? This second one needs something in front of it, which it has, but it needs to be 2 in front, yes? Doesn't have it. This second one did, this second one did. Understand? Okay, what about, let's see what's highlighted. Let's see, second one. How about this first one right here? I should probably underline what's staying. This guy's staying, this guy's staying. That guy went away. So far these two are going to stay, right? This first guy requires there to be a second guy over here. Is there one? Yes, it's there, right? So see, now I'm starting to develop the pattern that it looks like I'm going to get the telescopic canceling to happen. So since I see a pattern, I'm going to now write the nth partial sum. I'm going to establish the pattern very clearly, and then after I do that, I'll let n go to infinity and be done. Now I realize it's going to take up a lot of paper, so sideways, so I'm going to write in a smaller pen. My nth partial sum is going to be negative 1/2 over 3 plus 1/2 over 1 plus negative 1/2 over 4 plus 1/2 over 2. Can you all see that okay? Plus negative 1/2 over 5 plus 1/2 over 3 plus negative 1/2 over 6 plus 1/2 over 4 plus ... Now, I need to go out to n, right? The last one, which will be the nth one, and I need to pick up a couple in front of it also. But man, I don't know if I have enough space. Let me see. Let me try and go out to the last one. What would my last one look like? I'm plugging what into this? N. So it's negative 1/2 over what? N plus 1, and then plus 1/2 over n minus 1. The one right in front of that one, I'm just basically going to subtract 1 from each of these, right? Subtract 1. So you get negative 1/2 over n plus 1/2 over n minus 2. And the one right in front of that, negative 1/2 over what? N minus 1 plus 1/2 over n minus 3. That's your nth partial sum. Questions? Got 10 more minutes. All right. Let's cancel things out. This first one, we said should cancel with the second one 2 away, which was right here. Gone. There's their connector. That's the cancellation. First ones require something in front. So I don't have it. This one stays. First one cancels with second one 2 away. It should be right there, which it does. This becomes kind of a mess, doesn't it? These are gone. We said this second one will stay because there's no first one in front of it to cancel with. How about this first one? It will cancel with the second one 2 away. It should be right there. No, wait. I didn't write it, did I? But is it in here in the dot, dot, dot? It's in there in the dot, dot, dot. So we have to realize that this first one does cancel with something in that dot, dot, dot. And so it's gone. How about this first one? Same thing, right? It's got something 2 away to the right. It's going to cancel out also. I don't know where it is. I don't want to put arrows up there, but it's canceling with something in there. How about this first one? First one's cancel with, second one's 2 away. It should be over here. Is it right? Yep, there it is. That one and that one are going to kill each other off. All right, second ones require a first one 2 in front, right? Is this one going to go away then? Yes, because there is one 2 in front somewhere in the dot, 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 right? How about this first one? Right here. It requires a second one 2 away. There is no second one 2 away, is there? This one stays. I'm going to start highlighting the ones that are staying. This is staying. This is staying. This is staying. How about this second one? Goes away because there's going to be a first one 2 away in front somewhere in the dot, dot, dot. How about this first one? Stays. So that means S sub n is just this first yellow one, which is just 1/2, plus, then we have half divided by 2, that's a 4th, plus this other yellow one over here, which is negative 1/2 over n, and then plus another negative 1/2, but over n plus 1 this time. And so finally, the sum we're looking for is the limit as n goes to infinity of that expression. And it turns out to just kill off these guys at the end, right? And so all you're left with is 1/2 plus a 4th, which is 3/4. That's it. There's always one of these on a test, always. So one that you should try at home, because we are running out of time here, is sum n equals 1 to infinity natural log n plus 1 over n plus 3. What would be the first thing you do? Nth term. Nth term. What's the limit as n goes to infinity of this? Infinity over infinity here, right? Which means you would have to do L'Hopital. What's L'Hopital going to give you if you do that in here? You get 1, aren't you? You're going to get 1. What's natural log of 1? 0. Nth term test fails, right? This thing is going to the natural log of 1, which is 0. The nth term test fails. It's not geometric. It's not harmonic. So the only other thing we've got right now is telescopic. So we have to turn this into, we need subtractions in here, don't we? So how do you turn a log with division into subtraction? Split it, right? Use the property of logs. This is the same as natural log of n plus 1 minus natural log of n plus 3. Why don't we make this a take-home quiz? It's not that hard. We'll just make it a take-home quiz to be turned in next time. What I'm going to be looking for is that you do it the proper way. You know, write out, find the pattern, then write out S sub n, right? Then take your limit as S sub n, of S sub n as n goes to infinity, and then draw your conclusion. Not every telescopic series has to converge. Not every one of them does. All right. This is homework for this page 443, 7 through 28. Let me just verify that. Yeah, see how you do with those. Yep. Have a good day. Drop day's Thursday, remember. Check your grades online.